Oh, one more thing that I've been toying with. The final comes is on Monday, basically 3 days after test 4. So you learn that you get the test 4 results, and you basically have a day only. It's not great. So I was thinking if I clear it with the TAs and graders to ask on a piazza, I'm okay, like if we do this final test, I think in order not to interfere with any others, it will basically have to be in the evening. Whatever hours the last possible test, let's say it's 5 p.m. So it will be 5 p.m. on, it could be Wednesday, it could be Thursday. The thing is that, if there is some protest, like some people are like, well, I'm traveling that day, so, I don't want it. Well, if there is only like a handful, then I can still manage it, just arrange it separately with these people. But if there is more, then I will need to, then, it cannot happen. Right. So somebody says that, it's actually the TA, that a lot of students will have final course conflict. So that's why I think the only possibility is actually an evening. And, but, yeah. Just for section 10, but I'm talking about the final. Okay. Good. Oh, no. Yeah. Test 4 is chapter 10. There's some messages on the chat for people who are looking at on YouTube. Okay. All right. Oh, and yeah, so somebody is sending that, 7 to the third is 343. Yes, and you got a -1 point on that if you just wrote that on a test 3 without further explanations. Okay. Yeah. All right. All right. Good. Let's do let's go into the lecture, and we can talk about scheduling later, after the material. Okay. So let's chapter 12 starts probability. We have only one lecture left, so I thought I would do that because it takes all the counting stuff you did and moves it into the sort of a higher plane of probability, which is most useful. This is the most useful way in which you're going to encounter this material. And so probability is all over in computer science, right? In the life of a computer engineer, it's in testing, it's in modeling algorithm and behavior, it's in data structures that we look at. They are created with some randomness, social networks, internet behavior, many others. Also some things that are which randomness is absolutely crucial and necessary.
Oh,
like
God.
Whoever does that, please mute yourself.
Oh, sorry.
Sure. Okay. So here are the basic notions in probability. We talk about an experiment. The experiment is just some probabilistic process that leads to space of outcomes. We call that a sample space. And a probabilistic experiment chooses one element in the sample space with some probability. So a deterministic process chooses always the same thing. Probabilistic process has some range of possibilities from which it samples. So for example, sample space all poker hands, 5-card hands. When you're playing poker and somebody deals, this is the sample space from which you're getting your hand. Roll of a pair of dice in a game. If let's say that we're making some bet, or for some reason I want to flip a coin 3 times, so a triple coin flip, that's a probability space. It's like 3 bits. They can be all 0, 0, 0, 0, 0, or 1, 1, 1, or anything in between. The space is 3-bit strings. Or random choice of a, say, cryptographic key that has n bits, or for RSA, key generation and n bit prime, right? These are all sample spaces. And probability is a function that assigns every element in the sample space a value between 0 and 1. That value is the probability with which an element in the sample space occurs. So what are the constraints on this function? Well, first of all, probabilities are between 0 and 1. 0 stands for no probability. So if an element in the sample space has value P of that element is 0, that means that this element never occurs. When you run an experiment, it will never create this element in the space. You can just kick it out of the space. It will be equivalent, but sometimes it's useful to think of sample space and probability even 0 as meaningful. And a 1 is it's the opposite of that. If a probability of one element here is 1, that is the element that always occurs. So probability of all others are 0, because in general, when you sum over the whole space and look at the probabilities of each element in the space, you have to add to 1. The supposition here is that S was a discrete set. All this quarter we were talking about discrete mathematics. This is a set that has countable elements that are discrete and not a real line. Okay. So as we said, value, if the probability is assigned as 0, this means that this element never occurs. 1, he always occurs. 1/2 really stands for occurs roughly 1 in 2 times that I run the experiment. So if I ran it 2 times, I would expect one of them to hit value X. So that's why a coin flip, the probability of a coin flip is 1/2 tails, 1/2 heads. And the reason why we're calling them 1/2 is because if you do it many, many times, you will see that tails come roughly 1 out of every 2. And that's the source for why probabilities are between 0 and 1. Another way to say it is 50-50, right? Which is kind of, yeah, which is like 50-50. That's for X occurring and X not occurring out of 100. Yeah. So this is just something people say, but it doesn't correspond to our values, really. So a coin toss has these probabilities, right? And that's a fair coin toss. So if you have a correct coin that is going to flip tail or head with exactly probability 1/2 and not a cheated one. By the way, where COVID ends, there is a very cute museum of Indian and cowboy stuff in northeastern Los Angeles, after some actor who played in all these Western movies, and by Indian I mean Native American. Sorry. So one room has all cheating implements that were used by gamblers in the Wild West. All inventive ways of trying, of scraping a coin so that it has flips, of loading a die so that it flips to 6 more often than to the other side. It's brilliant, and you will be amazed by how many variety of these cheating techniques were developed. So a skewed coin is one that differs from the 1/2 probability. So, for example, a tail is 1 out of 10, and the head is the rest because they have to sum to 1, so it's 9 out of 10, right? It's hard to think like how physically you can have a coin like that, but you know, some probabilistic processes might be like this, right? Another example is a roll of a dice their sample space is integers 1 to 6. Each of them, if it's a fair die, has probability 1 in 6. But you might have a skewed die, like a loaded, like from that museum, where a 6 is loaded in some way, so it comes out twice more often than any other. In which case, the others have probability 1/7, right? Because otherwise it wouldn't sum up to 1. Okay, so these are sample spaces and probabilistic experiments. Now, an event in a subset in the sample space, that's another terminology. It might mean a single element in the sample space, but it might mean a set of these elements. So, for example, let's say that my sample space is 5-card hand. So it's a poker game. The dealer assigns to me random 5 out of the deck of 52. And if let's define an event that my hand has a pair of 8s. Okay, so there's a particular rank 8, and I want 2 of them, and I don't care which suit. So that corresponds to a set of elements in the sample space, namely all those that it's a subset of 5-card hands which have a pair of 8s. Okay, and let's say that I roll 2 die, and oh, Hagen, thanks, exactly, that's Gene Autry Museum, thanks so much. So you roll a 2 die, and a sample space is therefore, if the dice are marked, one is blue and one is red, so there is no confusion which one is which. So the sample space is the 6 square, 6 possibilities for each die, right? Cartesian product. So let's say that the event subset is that I'm considering all throw of dice where the 2 die created the same, came out the same. So I got a pair. It's a subset of my event space. Or let's say I flip a coin, so 3 coins. So this is my my sample space is triples of bits, head or tail, 0, 1 for a coin. And my event is that I get more heads than tails. The heads are 1, tails are 0. So in other words, the sum of the bits have to be at least 2. That's the only way I have more ones than zeros, right? Again, it's some part. I take a sample space and I partition it into subset that satisfies my constraint and the rest. And now, probability of an event is simply a sum of the probabilities of each element inside the event. So when you're saying, okay, let's say I roll a die, and it's a fair die, so therefore each x, each event has the same probability 1/6. Each element in some space comes out with probability 1/6. Let's say my event is I throw a die and I ask, what's the probability that it comes out even? Well, I look at the event even. What does it include? 2, 4, 6. These are only the 3 guys in the sample space that satisfy my constraint. And the probability that it occurs is just the sum of the probabilities over the x's in there. So it's 1/6 for each, 3, 6, 1/2. And it agrees with the intuition, right? That the probability that you get a even throw is exactly half. Let's say you have a skewed die, so the 6 is probability of 6 is 2/7, and the rest is 1/7. Now, even outcome, this equation changes because it's 1/7 for this, 2/7 for that, so 4/7, right? And of course it's skewed, right? Because the 6 is more likely. But how exactly it's skewed? Well, you can compute it. Let's consider distributions as they very often are, and they're the easiest to think about, is that the distribution over the experiment, the probability function assigns the same value to every element in the sample space. In other words, the experiment is you have some possibilities and you choose one of them at random with exactly the same probability. Okay, so when you're saying, okay, I'm throwing a bunch of random bits, n random bits, so every n bit string has the same probability. I'm casting a die, I have 6 choices, each one same probability, and on and on. What's the probability? It's 1 over the sample space, because that's the only way to satisfy 2 constraints. The sum of them has to be 1, and I'm summing over all in S, so therefore I'm summing this many things. And secondly, by the uniform distribution, they have to be equal. So now, if that is, if I'm dealing with uniform distribution, then to evaluate what's the probability of some event, okay, I plug my definition. I sum over all elements of the event, and I look at the probabilities. But the probabilities in case of a uniform distributions are 1 in the sample space size. So this is my probability. But summing over, but these are constants that are independent of x. Therefore, if I'm summing over this many of them, that's the quantity I get, cardinality of the subset over the cardinality of the subset space, of the whole space. And that's intuitive. If, here is all the possibilities, and say of bit strings that are random. And here is a subset called E of bit strings that satisfy some constraint. Then if I choose a random bit string, what's the probability that it satisfies the constraint? It's simply the size of the set that satisfies over the size of all. It's the fraction between the area that is the good one over the area of the whole universe. If my probability is to choose at random within the universe, then the probability that I hit the area I want is the size of the area I want over the size of the rest, right? You can pictorially convince yourself this has to be true. So let's look at some, you have a third die, so a uniform distribution over a pair of values from 1 to 6. And so you have 36 possible outcomes. And remember this formula for probability of an event. Let's say I have an event that says the sum of the dice elements is at most 3. So the good ones are only 1, 1, 1, 2, 1, 3 does not work, 2, 2 does not work. That's it. Yes. So what the oh, sorry, but I also have 0. So yes. So this is a funny dice. This numbered from 0 to 5 because of this notation. Okay. So if that was my die, numbered from 0 to 5 instead of 1 to 6, then the sum, then the event that satisfies this constraint is composed of this event, of this sample element of the sample space, these pairs. I just count them 10, right? 4 with the leading 0, 3 with the leading 1, 2 with the leading 2, and plus 1 with the leading 3. And that's it, that's my probability. Okay. For the die that starts with the 1, this would be 4, and you would get the same outcome. What is the probability that the red die has a higher number than the blue die? So my event is that the red comes out higher than the blue. Okay, I can count everybody inside, but here is the faster way using the bijection principle. Kick out all those which, so first of all, if blue and red are the same, then I'm kicking them out because they don't satisfy my constraint. So let's consider the subset, at least blue and red are different. And then within that subset, by the symmetry, you can consider look at the complement of the set within S prime. It's simply those which have a flip. The blue is larger. And by symmetry, bijection, the two sets, the set with larger red die and a larger blue die, have to have the same cardinality. So in other words, they're equal, and they partition the set S prime. So if the set has the red and blue are different, then you are either in here or in here. There's no other possibilities. So therefore, they have to be, the whole set is size 30. So each of these S prime and C prime and C prime and C have to have 15 elements. Therefore, the probability is 15 over 36. Okay. So it's less than half. Yes. But not, and equally, if I said, what's the event? If my event is that I want the blue to be, red to be at least the blue, not strictly larger, then I would add the 6 of equal in here. So it would change from 15 to 21 over 36. Okay. So I'm choosing a bit string, and I'm asking, okay, the first and the last flip come out head, but the middle flip is anything. Okay, well, there's only 2 possibilities, and therefore it's 2 over 8, because how many, all the bit strings I have, to the 3, which is 8. Okay, so this is 1 in 4, come out that way. And it's like clear that that has to be true, right? Because if my constraint, all the bits are independent, and I just constrain on the first bit being coming out head, so that's a 1/2 probability, and the last bit 1/2 probability. But let's see in a second what is going on. So this will be about independence of events, so it's worth revisiting. What about at least one flip comes up head? So that's easier to count by complement, right? I kick out the one that violates this constraint, which is an all 0 string, and then I see that the event is satisfied by 7 elements. So the probability of that must be 7 over 8. So let's say that it's a game deck, right? Like perfectly shuffled deck, and I'm taking a 5-card hand. So my sample space is all hands, 5-card hands, which is this large space, right? It's all possibilities of choosing 5 out of 52 in the deck. And let's say the event I want to measure probability of is some poker figure called full house. It means out of my 5 hands, 2 form a pair and 3 form a triple. And they have to be of a different rank, or otherwise you have 5 cards of the same rank, which is impossible. So you measure the size of that subset. You count how many elements satisfy it, right? So what's the counting? Well, I choose 2 different ranks. The first, and they're ordered because one of the ranks is going to designate the triple. The second rank will be the rank of the pair. And once the choice of ranks is, so therefore it's a 2 permutation of 13. And once that rank is chosen, then I have to specify the suit of the triples, card in the triple, and so there's 4 choose 3. and the suit of the pair of the cards in the pair. So therefore choose 2 because I'm choosing 2 cards of with the rest within the 4 cards that are of that rank of the 4 possible suits. So this is my formula. And what's the probability? It's the size of the set over the whole thing. You can compute it numerically, right? Like it's of interest. If you're playing poker, you will not, but at least you know how to compute it. Here is the kicking in of the counting by complement. You say your event is that I want to have a hand with at least 1 ace. Count hands with no aces, right? And the probability of so the cardinality of those with an ace is cardinality of all minus the cardinality of the no ace set, right? So note that let's see that the probability of getting an ace is all those with aces over the horns. By complement, you know that this can be rewritten this way. And now use the basic arithmetics to see that this thing is equal to, it can be written in this way. And of course, this part is 1. And what this is probability of the complementary event. And that is also clearly has to happen, right? When you considering a certain event and considering now the complement of that event, in this case, the event was I got a card with an ace, and a complement, my hand has no aces. The probabilities of these two have to sum up to 1 because they partition the space, and the probability of event P and an event P complement is nothing but a sum over the individual probability. So if you add the 2, this is the probability over the whole sample space, which is 1. This is easier to count. We are not doing it here. You can do it. So you can also do, palindromes, probability, just because if you can count, then if you can count how many elements are in your set, that is your event set. So and you can count what is your sample space. So you know what your sample space are, random bit string of length 7. You know what your good events are, which is all palindromes within them. And the string is random from the sample space. So we are talking about uniform distribution. Then that's enough to compute probability. You count how many elements in the sample space, you count how many in your events, and you divide, and you know the outcome. So say you taking a random string over some alphabet, and you're asking what's the probability that there ever is a consecutive repeat. So your sample space is 4 to the 10, 4 possibilities, but you are 4 elements. You're getting a 10 long string over them. So that's the sample space size. What's the complement? Is that the complement of having some consecutive repeat is, of course, having no consecutive repeat. That is an easier thing to count because I have 4 choices for the first element, it's 3. But after I choose the first element, in order to have no consecutive repeats, the second element is chosen freely from a constraint space that has the first element kicked out. right? Because I cannot have a consecutive repeats. If my first element was A, I'm choosing from BCD. If my first element was B, then I'm choosing from ACD. Does not matter. I always have 3 choices. And that will recur for every subsequent character taken. I'm choosing always from a space that includes the original alphabet minus the previous character in a string I chose. So that will occur, the same space will be, the same number of choices will function at every move from the second element of the sequence to the last. So that will be 9 choices like that. So this is the cardinality of the set. And you know, in order to compute the probability of the complement of that, I just subtract, right? So it's 1 minus the probability of this guy, which is 4 times 3 to the 9th over 4 to the 10th. Okay. I'm going over the, because there are also like another examples of counting and like kicking in some counting by complement. But here is it's a novel, it's a you know, taking it with another concept that relates to probability. It's often useful to think to be able to tell whether 2 events in the sample space are independent or not. Okay, so let's say in a cryptographic context that you have some one event, which is that you observe certain ciphertext on the wire. You're an attacker, and there is another event, which is that corresponding plaintext was sending some message that you would like to learn what that was. If a cipher has a property that the event observing certain ciphertext and the event that the plaintext was some string were independent, that's a good thing for crypto system, because that means that what attacker sees ciphertext is independent of what the underlying plaintext was. So this is actually a notion that Claude Shannon defined as perfect security for encryption, and it's intuitive that it would be observed ciphertexts are independent of the underlying plaintext, so therefore there is no information to be gained about the plaintext if adversary just observes ciphertext. What is the notion of independence? This is the definition of 2 events being independent. If it is the case that you can compute probability of the 2 events occurring at the same time. In other words, what does it mean 2 events occur at the same time? I'm choosing from one sample space. Events are subset of the sample space, because if I think of the probabilistic experiment of encryption as a whole, including what message was chosen, what key was chosen, and how does the encryption run to create a ciphertext, if I include all that space, that's the space. And some events within that space corresponds to the message being that, and some events in space corresponds to ciphertext being that. What I have to look, what's the intersection between these 2 events? In other words, in my case, this will be that the message was this, and the ciphertext was that. And if this intersection, probability of such an intersection is equal to probability of first event multiplied by probability of the second, then I call these 2 independent. Let's look at some examples of, you know, to put an intuition why that would be, that that this is the notion of independence. Okay, it is not immediate, like that this means that the 2 events are independent. Okay, so let's try to gain some intuition about it. Let's say the sample space is that I choose 2 bits, x0 and x1, and my events are The first event is that x0 comes out tail. The second event is that x1 comes out tail. If I'm choosing a random bit string, therefore I'm choosing 2 bits independently. I'm choosing the first bit 0, 1 with probability 1/2 each. The second bit 0, 1 with probability 1/2 each. So clearly they are intuitively independent. And indeed, this notion captures that, or at least it comes out correctly in this case, right? Why? Because if you're choosing 2 bits, what's the probability that the first one comes out tail? It's 1/2, because half of the elements in here have this probability, namely all those 2-bit strings whose first bit is 1. The other bit can be either 0 and 1, so there's 2 of them. And how many choices of 2-bit strings you have? 4. So it's 2/4, which is 1/2. And the same thing for restricting so that the second bit is 1. So what's the probability of intersection? Well, it has to happen that the bit string I chose satisfies this constraint, so it falls into the set of those bit strings whose first bit is 1, and also falls into the subset of bit strings whose second bit is 1. Well, there's only one bit string like this, whose first bit and second bit are both 1. So clearly, this probability that the random bit string is equals 1, 1 is 1/4, because there's 4 bit strings and this is a fixed one. So boom, you have equality. You would say that yes, these 2 events have to be independent. If it's a random bit string, then each of its bits is chosen at random. What's the big deal? Well, the big deal here is to just verify that this definition, was correct, was agreed with our intuition, at least in this case. Now let's do something a little trickier and consider the same event for first bit. The event A is still that the first bit is 1. The second event is the XOR between these 2 bits is 1. Now it's not so clear that these are independent, because the first event depends only on the first bit, but the second event depends on both. So the second event, in some intuitive sense, depends on the first event, because the first event depends on x0, B depends on x0, so B depends on A. Okay, that's one notion of what does it mean to depend on, but we have this notion. Okay, these 2 sets might be non-intersecting, right? They have some non-intersection. Who knows how, in general, how these elements in the sample space are chosen? Perhaps some of the elements are plain text, which come out from human text. So, they are distributed in a very non-uniform way over English sentences. Okay. Perhaps the second event is choose of a key, which is random. Perhaps the third event is choice of how sorry. I have to kill. Yeah, sorry about that. Okay. Perhaps the second event is a choice of a run of an encryption algorithm that depends on both the plain text and the key. So there are dependencies between elements in the sample space. That's the dependency example of the kind of dependency. And yet, these 2 events are independent. Here's why. So the probability of the first bit being 1 does not change. It's the same as on the previous slide. What's the probability that the XOR between 2 bits is 1? Well, the XOR of the 2 bits is 1 if the bit string is either 0, 1 or 1, 0. In all the other cases, 0, 0 and 1, 1, the XOR between the 2 bits was 0. Okay, so that didn't satisfy this. Because there's 2 bit strings that satisfy this constraint, the probability of this event is 2 over 4. So 1/2. Now let's see what's the probability of the intersection. In other words, what are the strings such that the first bit of it is 1 and the XOR of the 2 bits is also 1? If you look at the intersection of these two, there's only one element in it. It's this bit string. It has to start with a 1 in order to satisfy this constraint, and the second bit has to be 0 to satisfy this one, given that it satisfies that one. So therefore, the probability of both of these events occurring is 1/4, and the equality holds. To see that this notion makes sense, the best way to see is to look at the conditional probability, and which is the following. So in some sense, in this example here, what the attacker wants to know is, well, here's some probability of, there's some inherent probability of people sending a message like this. The question in the attacker's mind is that he observes a ciphertext, and now, given this ciphertext, so given that from all choices of people sending message and keys being chosen and encryption execution, the subset of these possibilities is now constrained to only those created the ciphertext that the attacker observes. And his question is, did this event influence the probability that the person has this message? Or is it the same as it was before I even saw the ciphertext? So therefore, the ciphertext is useless to me because it doesn't change my assessment of whether or not this message was sent. That is expressed by something we call conditional probability. We express it as probability of event B dash A, which is read like this. It's the probability of event B conditioned on event A happening. In this case, probability that this was the message, given that the ciphertext hit this particular value we observe. The conditional probability is defined as follows. It's the probability of the intersection between the two events divided by the size of the probability of this event occurring. Pictorially, it's like this. You have a big sample space, and within it, you have some probability of event B. Now you have this event A occurring, like a ciphertext, you observe some value. This means now you scale down the picture. You're not interested in the whole sample space. You're just interested in in what happens within all choices satisfied event A. And if you scale down, and now this becomes your universe, then the probability of event B happening that this is what you observe is, well, you're not concerned about B outside of A, because that's not your world anymore. Your world is just intersection between B and A. And what's your sample space? It's now restricted to A. So this is a natural generalization of, at the beginning, you have a big sample space, there's nothing happened yet, and you just choose, and you just choose a sample, and the question is it inside of some event or not? but let's say it was conditioned on a sample space being essentially reduced to some subset A. And within that subset, how many are still within B? That's this part. And how big is this A? So in other words, what's the fraction of A that is occupied by elements of B? That's what this really measures, right? If you think of uniform distribution, then these map into just fractions, sizes. But it's more general than that, because the distributions don't have to be uniform and it still makes sense. But if these are uniform distributions, then and simply probabilities of any events are just sizes, then the conditional probability is simply the size of the intersection over the size of the set you're conditioned upon. Okay. Well, I will go through this. It will be my final slide with some crypto application. I'm running a little bit. No, I'm not exactly running behind time yet, but I will in 5 minutes. Okay. Good. So let's consider uniform distributions, and in which case the probability will simplify to the sizes of the intersection over size. Okay. So let's say I have this thing called shift cipher that we had a few weeks ago, right? And so n is some public modulus, and the message is encoded as a residue mod.n, right? So a value between 0 and n-1. N can be the size of the alphabet, if you will, and m is an element, it's a character from that alphabet. K is uniform, key is chosen uniformly in that space. So it's also a uniformly chosen modulus. Message is not uniformly chosen. It can be encoding, I want to sell IBM stock. Very non-uniform, right? Or I want to buy IBM stock, let's say. So the key is uniform. And the encryption is the shift cipher. What did it do? It just added the encoding of the message mod n and the key, which was the random value mod n. Decryption inverted that by subtracting the key. Now consider the event B. For this to make sense, there has to be some uncertainty. Is he sending sell IBM or not? Let's consider a very simplified scenario. There's only two messages possible: sell IBM, buy IBM, and let's say with probability 1/2 each. So before you see the ciphertext, you don't know, is this guy selling or buying? Let's see if observing the ciphertext changes this 1/2 probability between the two. If it doesn't, that would be a good thing for this encryption. And it doesn't, because the probability here is, so the A probability is that you observe certain ciphertext, reduction of the space to some subset. It's your observation. And the B is this question. The question is he selling IBM or is he not? So we are concerned with, we want to compute, where's my pointer? The probability of the event B after observing event A, in other words, that the ciphertext hit per certain value. Let's say that n is very large, so this is a very large value, okay, possible, because n here is, higher than 16 to the 8. So what is this conditional probability? Okay, well, let's compute the probability of this event and the probability of intersection between the two. And probability of this event is the probability that a certain ciphertext happens. Now, I can rewrite this knowing that my encryption, what my encryption does. The probability is that m plus k equals c star. The probability goes over random choices of m, one half this, one half that, and a random choice of k, random in the end. If I rewrite this constraint this way, then it is clear that no matter how m is chosen, if I choose k, it's exactly 1 over n possibilities that it equals this value, because k is chosen uniformly in the n, so it collides with this value with probability exactly 1 over n. That is true about shift cipher. Okay, now let's look at the intersection. What's the probability that that a message hits this value and that it encrypts to this C star value that is observed? Okay, let's look. First of all, replace the encryption condition with the arithmetics. So this equation means k plus m star equals c star. I can just put m on the other side, and I have that the key is the difference between c star and m star mod n. Now, if I knew that these two independent are independent, then I could rewrite probability of intersection with the product of probability here and probability here. Why are these two independent? Because key is chosen uniformly independently of the message, right? That's clear. Every encryption has to work like this. The key is chosen independently of what you encrypt. So I know that key equal whatever, the probability of that this event is independent of the message. So I rewrite this as the product of this probability and this probability. And now, boom, this is 1/2, and this is 1 over n. So the total probability of this intersection occurring is 1 over 2n. And because the conditional probability is the probability of intersection over the probability of this reduced domain, I have 1 over 2n divided by 1 over n, and I have 1/2, right? So this is very, very close, by the way, to the whole argument a few slides back about how one bit and the XOR of bits are independent. Here I have not a bit, but a character in the n. And here I have not an XOR, but an addition mod n. But XOR is nothing but addition mod 2. So it is not surprising that it generalizes to computation mod n. It is independent for the exact same reason that if you will, this is like the second bit in the 2-bit scenario. This is the first bit, this is the second bit, and the constraint is that they have to have certain XOR. That constraint is now replaced by having to satisfy certain arithmetic addition mod n. Okay, but that doesn't change anything in the argument. Okay. Okay. You know, I just wanted to get to this little cryptography application of counting and probability and conditional and dependent. This was an incredibly fast introduction to the topic. I will require you to read about the first few sections of chapter 12. As I said on Piazza, you can read them after the exams, so you know, read them with some peace of mind rather than stress that it takes away your time from other finals, and that applies to everything else. that you still haven't read and you need to make up. And this, well, if you take an undergraduate crypto class, obviously you do this. If there is probability classes, there is statistics, and there is classes, further classes that, in computer science, where you will encounter probability in probabilistic algorithms. I believe that's CompSci 46, or it's algorithms basically class, and if you take anything about artificial intelligence, machine learning, you have a probability galore and statistics. So you will revisit these concepts, but I want you to finalize all discrete math stuff with learning a little bit more now when it's fresh in your memory, so that when you revisit this in other classes, this will be you will have some already some comfort with this notion. Okay, and I will stop recording. So thank you for participating in the class, and then I will take questions maybe offline, because maybe that's easier for people to ask any. Okay, thanks for watching.